Unified, SDN ready, key technologies in IPoDWDM. In an IPoDWDM architecture, the magic happens by shrinking traditional room-sized optical transport equipment into small, pluggable modules that fit directly into high-capacity routers. Here are the key technologies that make this possible. 100G/400G/800G IP/MPLS routers. These routers are the brains of the operation. In an IPoDWDM setup, the router is no longer just responsible for packet switching, it must also manage optical parameters. High-density line cards. Modern routers feature ports designed for QSFP-DD or OSFP form factors that can handle the high power and heat of coherent optics. Unified control plane. The router's software, like Cisco IOS XR or Nokia SROS, communicates with the optical pluggable to tune its frequency, wavelength, and monitor its health, OSNR, power levels. 2 coherent pluggables, DCO. This is the single most important technology in IPoDWDM. It replaces the traditional standalone transponder. QSFP-DD/OSFP/CFP2, these are the physical form factors. QSFP-DD is the most popular due to its high density. Digital coherent optics, DCO. Unlike old gray optics, DCOs contain a DSP, digital signal processor, chip. This chip compensates for fiber impairments like chromatic dispersion, CD, and polarization mode dispersion, PMD, in the digital domain, allowing signals to travel thousands of kilometers without needing physical compensation hardware. 400ZR and 400ZR+, these are the industry standards. 400ZR is for short-reach data center interconnect, up to 120 kilometers, while 400ZR+, and OpenZR+, offers higher performance for long-haul regional and core networks. 3. The optical line system, OLS. Even though the transponder is gone, the road, the fiber path, still needs infrastructure to combine, direct, and boost the light. DWDM MUX/DeMUX, multiplexer/demultiplexer, this is a passive device that acts like a funnel. It takes multiple different colored light signals from various router ports and combines them into a single fiber core. At the other end, the DeMUX separates them back into individual colors. ROADM, reconfigurable optical add-drop multiplexer. A ROADM is the smart traffic intersection of the optical world. Remote management, it allows operators to remotely change which wavelength goes where without sending a technician to move cables. Wavelength routing, it can drop a specific color at a local city or pass through other colors to the next city entirely in the optical layer. FlexGrid, modern ROADMs allow for flexible channel spacing, meaning a 400G or 800G signal can take up a wider slice of the spectrum than a standard 100G signal. Optical amplifiers, EDFA and Raman. Since light loses strength as it travels through fiber, it must be boosted every 80 to 100 kilometers. EDFA, erbium-doped fiber amplifier. The standard booster. It uses a laser to excite erbium ions in a special piece of fiber, which then transfers that energy to the passing data signals. It is cheap and efficient but adds a bit of noise, ASE. Raman amplifier, a more advanced distributed amplifier. It uses the actual transmission fiber itself as the gain medium. It is often used for very long spans because it provides better OSNR, optical signal-to-noise ratio, than EDFAs alone. Summary of technology roles. Technology role. Traditional location. IPoDWDM location. DSP/coherent compensates for fiber inside transponder inside pluggable logic distortion shelf, router, combine/splits MUX/DeMUX optical shelf OLS, wavelengths ROADM directs wavelengths optical shelf OLS. Technology role. Traditional location. IPoDWDM location. EDFA/Raman boost signal strength optical shelf OLS. Applications of IPoDWDM. As of 2026, IPoDWDM has moved from being a specialized hyperscaler-only tool to a mainstream architecture used across various segments of the global internet. Its deployment is primarily focused on areas where bandwidth demand is massive and physical space is at a premium. Here is a summary of where IPoDWDM is currently deployed. 1. Data Center Interconnect, DCI. This is the most dominant use case for IPoDWDM. Hyperscalers, companies like Google, Meta, and AWS were the early adopters. 4. They use IPoDWDM to link massive AI factories and data centers within metro areas, typically up to 120 kilometers apart. AI training clusters. In 2025 to 2026, the rise of large-scale AI training has led to scale across DCI, where IPoDWDM links are used to create massive virtual pools of GPUs across multiple physical buildings. 2. Service provider core and metro networks. Traditional telecommunications companies, telcos, are now following the hyperscaler lead. Network modernization. Major carriers, such as Telefonica, AT&T, and Deutsche Telekom, are replacing legacy transponder shelves with 400ZR+ and 800ZR+ pluggables in their core routers to reduce costs. Metro aggregation. IPoDWDM is being deployed in citywide networks to aggregate traffic from residential fiber, FTTH, and business services directly into the core, bypassing traditional transport layers. 3. 5G backhaul and edge computing. IPoDWDM is a key enabler for the edge cell site aggregation. As 5G traffic grows, traditional microwave or low-capacity fiber is being upgraded. IPoDWDM allows 100G or 400G colored optics to be plugged directly into cell site routers. Multi-access edge computing, MEC to keep latency low for applications like autonomous vehicles or AR/VR. IPoDWDM connects small edge data centers to the main network with high-speed, direct optical links. 4. Regional adoption, global snapshot, North America, currently the largest market due to the high density of hyperscale data centers and early 400G adoption. Asia Pacific, China and India the fastest growing region. China is using IPoDWDM extensively for its massive 5G infrastructure, while India is seeing a surge in DCI build-outs. Europe focuses on energy efficiency and sustainability. Many European operators are adopting IPoDWDM specifically to meet green IT goals by reducing the power consumption of their central offices. Summary of deployment use cases. Primary deployment area. Why IPoDWDM? Technology. DCI, Metro, 400ZR/800ZR lowest cost per bit, extreme density. Simplifies management, multi-vendor telco core 400ZR+/800ZR plus interoperability. 5G backhaul 100G/400G DCO handles massive cell site traffic with low latency. Enterprise/400ZR plus ultra low latency for high frequency trading. Finance. IPoDWDM vs traditional IP over SONET/OTN. Comparing IPoDWDM to traditional IP over SONET or IP over OTN, optical transport network, is essentially a look at how the internet has moved from telecom-centric designs to data-centric ones. While SONET and OTN were built to wrap different types of traffic, voice, video, and data, into managed containers, IPoDWDM aims to remove those containers entirely to gain speed and efficiency. The evolution of the stack in a traditional network, the path a packet takes is a multi-layer sandwich. IPoDWDM flattens this. IP over SONET feature IP over OTN, standard, IPoDWDM, modern, legacy, data optimized digital router integrated philosophy voice optimized, TDM, wrapper, collapsed, high, many gray fiber high, many gray fiber interconnects 0, direct colored light, patches, high, standard maximum, direct IP to efficiency low, high overhead, FEC/OAM, lambda, router plus SONET ADM plus router plus OTN switch plus hardware router plus passive MUX DWDM 1. IPoDWDM versus IP over SONET. SONET, synchronous optical network, was the king of the 1990s. It was designed for steady, predictable voice calls. The cell tax, SONET has fixed size frames. When carrying bursty IP traffic, it is very inefficient, much like trying to fit various sized boxes, IP packets, into identical rigid crates, SONET frames. Speed limits, SONET essentially topped out at 10 Gbps, OC 192. Moving to 100G or 400G with SONET architecture is physically and economically impossible. IPoDWDM advantage, it eliminates the SONET layer entirely, removing the rigid framing and the expensive add-drop multiplexers, ADMs. 2. IPoDWDM versus IP over OTN. OTN, optical transport network, is the digital wrapper used in most carrier networks today. It improved on SONET by being built specifically for data. The demarcation debate, in a traditional OTN setup, the router sends a gray signal to an OTN transponder. This provides a clear demarcation point, the IP team manages the router, and the optical team manages the transponder. Management complexity, OTN requires its own management system, power, and rack space. It adds latency because the signal must be wrapped and unwrapped at every hop. IPoDWDM advantage, by putting the OTN logic, the DSP, inside a router pluggable, you save roughly 20 to 40% in capex and significantly reduce power. You lose the physical box demarcation, but you gain a unified software-defined view of the network. Summary of key differences. 1. Bandwidth and scalability. Traditional, OTN/SONET scaling from 100G to 400G often requires buying entire new shelves of hardware. IPoDWDM, scaling often just means swapping a pluggable module in the router. 2. Latency. Traditional, every layer, OTN/SONET, adds microseconds of mapping delay. IPoDWDM offers the lowest possible latency because the router's ASIC speaks directly to the coherent optical processor. 3. Protection, resiliency. Traditional, relies on hardware protection, example SONET UPSR/BLSR rings, which switches in 50 milliseconds. IPoDWDM relies on IP layer restoration, MPLSTE or segment routing, Point 8. While slightly different in logic, modern IP rerouting can now also achieve sub-50 ms speeds without needing dedicated standby fibers.